So we start this second session, and let me say that I'm happy for the organization of this important workshop, but I'm even happier because this gives me the possibility to come back to the places where I was very familiar 10 years ago, and so I'm moved also of seeing many colleagues from Torino. So thank you. And now, and also now we start with the first talk, which is I think very creative must be, because it starts from curiosity-driven exploration. So these are magic words. It is by Pavlo SOLOKHA dell'Università di Genova. Thank you.
Thank you very much. It's just 1 year ago that I received a kind invitation to participate on this beautiful conference on quasicrystals and approximants. So thank you for having invited me. And I would say that all my scientific life I worked with intermetallics. And currently I am conducting my research at University of Genova, and I'm still doing intermetallics. So I would like also to highlight that me and quasicrystals, we are peers. We have almost the same age. In this, from the beginning of the discovery of quasicrystals, they published thousands of publications, a plethora of publications, also dealing the fascinating physical properties of this. And as you know, any property of solid-state material depends on crystal structure. So I would speak mainly about crystal structures, and I would mention also that the discovery of quasicrystals induced also the UPAC to change the definition of what is quasicrystals, what is crystalline materials in general, and now it's any structure with an essentially discrete diffraction pattern. But it's only in 2007 when the first complete structure determination of ytterbium-cadmium icosahedral quasicrystal was done by Tsai and co-workers. It also due to the intuition that triacontahedron, this polyhedron you can see here, is a fundamental building unit, and his aperiodic distribution within the crystal space is a key role in the formation of quasicrystals. The empty spaces between these triacontahedrons are fulfilled by oblate and acute rhombohedron. Okay. Let's also think about where quasicrystal forms, and a beautiful picture with a periodic table you can see here with the yellow marked elements that are taking part inside of quasicrystals. And as you can see, it's almost all the metals of periodic table. Mainly these are binaries or ternary combinations where we have rare earth elements combined with late transitional elements. It may happen rarely that the range of existence of quasicrystals are quite extended concentrational region, but it also happens that these quasicrystals have quite point composition. It's also true, and probably the most lucky phenomenon also, that frequently quasicrystals are accompanied by satellite compounds, normal periodic 3D structures that are called approximants. Well, and as Sander already explained beautifully about superspace approach, I would like to highlight also its impact into the crystal structure solution of quasicrystals. It's not an easy task to explain this approach because it deals with a high-dimensional superspace, but with this plot, I would like to make some comparison between two-dimensional and one-dimensional structures. Let's imagine to have a periodic 2D structure, where in red you can see the unit cell dimensions, and these lines represent so-called atomic domains. If one will construct slope section of 1 over tau slope, we can get an aperiodic sequence of LS and S indicated here, so we will get an aperiodic structure. But what will happen if we will construct another sections with different of 1 over tau section? For example, if we will construct 1 over 1 section or 1 over 2, we will get even similar but periodic structures, and it becomes obvious also the relations between the structures of quasicrystals and approximants. They are constructed of similar building units, similar atomic domains. And here, just to remind you what is a satellite, and it was a very important point for me, and my discussion will concern approximants. As a title of example, here you can see the structures of two approximants of 1 over 1 and 2 to 1 type, and you can see that their crystal structure are very similar, are not the same, but very similar. The inner part of this polyhedra here are almost the same, but the packing and the gluing atoms are somewhat different. Well, so up to now, all the approximants, they were grouped in 3 main groups according to the name of discoverers, so Bergman, Tsai, and Mackay type. All these clusters contain onion shells with icosahedral symmetry, but probably in different sequence, one after another. And I will just mention some very important solids inside, like icosahedron, dodecahedron, icosidodecahedron, and the buckyballs, some derivative of rhombic triacontahedron, and essentially a rhombic triacontahedron. Historically, mainly Bergman and Tsai types approximant and quasicrystals were discovered more, and the idea of how they are constructed were much more studied and developed. In these compounds, you frequently see these RTH clusters that are B-linked when sharing the phase or interpenetrate each other, giving so-called C-linkage. What about Mackay clusters? There were a lack of information, also probably due to the very highly disordered structures with many defects, with many distortions, split positions, but clear indication of what is happening here, far from the center, were not given. I will try to fulfill this empty, and with this slide I wanted to show you some evolution of rhombic triacontrahedron, that is common structure in 6-dimensional space of quasicrystals, by very simple procedure of eliminating the vertices. So when doing so, we will get some shell with less number of atoms, but we will get some point symmetries that are now compatible with 3-dimensional periodic structures. For example, here we have 8 atom less, here we have 16 atom less, and so on and so forth. Anticipating, I will tell you that this polyhedra you can see in the bottom is a fundamental building unit of the approximant we discovered here. Well, the work, all the story of this investigation you can read in this paper, and it's a very pleasure to me that 2 of my co-authors, Rena De Negre and Davide Proserpio, now is here present in this aula. Okay. When we start our investigation, we were wondering about one very fundamental point: how one can find a group of compounds with a certain structure characteristics, such as a Mackay-type cluster with an ever-growing databases. Before I will start this story, I want also to give you a question. For your opinion, the molecules I show here, are they different or they are similar? Probably any of you will tell me that they are completely different. They are the combination of different atoms. The distribution of these are also different, but they have a very similar feature. They have the same number of symmetry elements. They all are of C to V point group. And this set of symmetry elements, when translated in 3-dimensional space, it's what usually we use when screening databases. When we use it for looking for searching for such a compounds, we usually put information like space group, week of sequence, number of atoms, etc. All these are symmetry properties. And For example, I give you here two compounds that have the same symmetry properties, but they are completely different. One of these, a binary, another ternary variant, is here we have a flipped position of cations and anions and so on and so forth. So one more point I will highlight here, and probably any of you will see the same structural unit for these sulfates and selenides. It's a molecule of the same shape and same topology. But the crystal structures that are guessed in these molecules are completely different. So this example is exactly the same, but concerning approximants. We wanted to look for different structures, but that contain the same structural feature, Mackay cluster inside. Obviously, the group theory is hardly be of use here, and you should use some alternative approach. We decided to exploit the graph theory for doing that, because it's somewhat have less connections to the symmetry properties. It's about topology and coordination. So we realize different algorithms for doing this. We scroll all the database of inorganic compounds of more than 220,000 of compounds inside, and we found 242 compounds that contain Mackay clusters inside. When doing some geometrical constraints about interpenetration, etc., we filtered more, and we achieved only 52 entries that were pure Mackay approximants containing Mackay clusters. What about the chemical composition? All these 22 compounds contain like cations or magnesium or scandium or zinc or aluminum, and the other components are usually transitional elements. When going further, among these, 19 are of 2-to-1 type and 33 are of 1-to-1 approximant type. When analyzing the topology of distribution of these Mackay clusters, we can tell that all of these are very similar. They fall in one of these groups, or base-centered cubic network topology, or face-centered cubic topology, or primitive cubic topology. Okay, and later we analyze the chemical composition of the most abundant group, and you can see that many of these contain scandium like a cation. So we decide to target our experimental part, focalizing on scandium like one component, and we look for another one. A best choice was palladium for several reasons. Between scandium and palladium you have a good X-ray scattering contrast, so it's an excellent example to suppose for structural investigation. With palladium is similar, it's also the element like other components of this set. And in literature, it was already present, the data about existence of this compound, but no structural data were published. What is more, the AFLOW algorithm give you possibility to construct immediately a convex hull, and what was of interest that in this binary system, there were no indication about the existence of any compounds, probably because of the lack of crystal structure. So we decided to make a synthesis. It was enough just 2 samples to prepare by arc melting to confirm that this compound exists, and the average composition is close to 5615, and the temperature of formation also similar to what was published in literature, and we have an excellent crystals inside of the sample, so we decided to go further with structural investigations. There were no problem. This structure is periodic one, it has an orthorhombic symmetry. You can see the excellent residuals we received for the crystals, and as it was supposed before, we have a Mackay clusters inside with palladium, later 12 atoms of scandium, later 30 atoms of scandium equals the dodecahedron, later palladium again. But what is most important, the outer shell, it could be defined as a defect triacontahedron with scandium-68, palladium-8 composition. Even in this case, we have a simple BCC topology of the packing of these clusters, and if you will separate them a little bit, you will recognize also the same idea of connection between them, the B-type and C-type connection between these clusters. So probably many of the researchers will stop the investigation here because you got an excellent result. But there is some point, and I want to make attention on the anisotropic displacement parameters for the different shells we can envisage in this cluster. You can see that they are perfect in the inner shells, but they are somewhat different in the outer shell, and we have several positions like scandium-9 and scandium-13 that show you some cigar-like anisotropic displacement parameters. We picked several crystals, but all of them show the same tendency to have this behavior for the ADP parameters. So this feature is somehow intrinsic one of these materials. When refining the chemical composition, this scandium-9 position was modelized like a mixture of two, scandium and palladium, and you can see that another crystal gives a somewhat different ratio between this. The scandium-13 position was split in three different, constraining them to be fully occupied. But if you know something about crystallography and you know that palladium is a heavier atom, the same situation you can modelize with palladium partially occupied here and palladium partially occupied here. So the question arose, who sits where? What is the correct chemical composition for this binary compound, only two elements combined between them? We proceed further. We use the maximum entropy method to reconstruct good quality electron density maps. And as it was already highlighted in the first shells, we have very sharp and spherical peaks for electron densities, but some problems become obvious in the outer shell of our clusters. And again, we have this cigar-like behavior for scandium-9 and scandium-13 positions. Okay. Even more, we constructed some differences plots for spherical model and from MEM method, and we construct some different maps just to highlight that for two crystals, the scandium-9 positions behave somewhat differently. What is more, some difference plotted were constructed for charges evaluation of different species, also comparing by DFT calculations. They all have the same similar trend, but the scandium-9 and palladium-5 positions strike in the eye because of the out-of-trend behavior of this. Sincerely speaking, there is no method, experimental method, to elucidate more on chemical composition at this level. Neither TEM can help you, neither electron diffraction, neither spectroscopy methods. So we decided to move down using DFT modelization. And I will start a new chapter here. We are speaking about binary compound, where on the structural point, from the structural point of view, you can modelize somewhat composition by doing only three different mechanisms of introducing vacancies, or either you can substitute elements between them, or you can combine these two scenarios between them. Just to illustrate you, I propose our structure to simplify somehow with two positions of species 1, species 2, and the rest of compounds that are of no interest for us. Let's imagine wanted to put inside one defect or vacancy or substitution. With this picture, you can see that there are 4 different scenarios for doing that. Obviously, DFT calculates under rigorous periodic conditions, so you are obliged to eliminate all symmetry elements and to move to P1 space group. So you have exponential explosion of your models for doing that. But if you wanted to make some irreducible representation and restore some symmetry elements, you will get some reduced subset with ordered models inside. So this works so with only one defect introduced into the structure. We did the same with our clusters. We tested all the positions inside the structure, introducing only one defect inside. And from this plot, but also consider that multiplicity of the sites we are testing are different, so we will get some structures that have different chemical composition also. To have some energy cost value, we decided to use a convex hull as a reference point for this. And you can see that the introduction of vacancies in the inner shells have a very high energetic cost, so they are highly defect resistant. Instead, the outer shells are more favorable for Guestin defects. For example, scandium-9 side give even negative values with respect to convex hull, and the similar behavior is also seen for scandium-12 position, but differently for our experiments, no hints from this plot for scandium-13 position. We decided to go down, to explore these two scandium-9 and scandium-12 positions for introductions of vacancies. And this time the topic is a bit heavier. You can see from this illustrative scheme what will happen if you will consider two defects introduced in the same structure. And you can see that you can realize it in this way, that one, this one, and 27 more other scenarios. So your P1 subset will contain a big amount of data, of models. You can reduce it somehow in configurational, compositional space later. When projection everything to our approximant, we limit our defect introduction to 8 only per unit cell. And you can see how big set you will get. And also the reduced subset contain more than 1,700 structural models. It's too heavy to be elaborated computationally, so we introduce also some random selection criteria to reduce a number of models to 1,000. After that, all these 1,000 models were calculated the energy of this, and all these were plotted to the convex hull. I should make some comments on this. The most favorable energetic model was 5516 composition, and experimentally deduced 5615 is situated somewhat above, but it's less favorable energetically. There are also many other red dots here that are very close to convex hull, and the difference between many models here are only a few milli-electron volts per atom. So, if I will take some structures from this area, for the scandium-9 position, it was confirmed that the defect introduction is really energetically favorable, but scandium-12 position is not so favorable, so we can neglect this scenario. What is happening better is scandium-9 defect introduction. For these models, when you will pick up some snapshots of zone of interest, you will see that introduction of defect in scandium-9 or palladium in scandium-9 induce splitting of scandium-13 position. After the geometrical relaxation, the position of atoms move a bit. When reaching these points, another question arose. Obviously, the experimental part you are doing not at 0 Kelvin conditions. It's an elevated temperatures. So, may it be possible that our structure is something average in fact, because we have many models with similar energy. So we decided to pick up all these structures which were close to convex hull, merge them in the space group EMMM of our approximant, and to see what is happening later. And please glance on this picture. After doing that, we get the very same situation like we observed from the MEM maps for our approximants. So probably this situation also opens some philosophical discussion what is a point compound and what is a solid solution. It blurs the horizons between them. And we have no answer for a moment for this. But anyway, the match between experiment and theoretical deduction are excellent here. It's not the end of the story. We also decided to make a step behind and to analyze a bit more our set of approximants. Here you can see the traditional maps that were used for intermetallics, like Pettifor maps, where some isles with the existence of some stoichiometries and some structural properties were constructed for combination of elements with different Mendeleev numbers, in other words, with different electronegativities. It's the only parameter was used to construct these maps. The very similar was used later by Storer when predicting some combinations for new quasicrystals' existence, the only electronegativity parameter. We decided to explore more and more focused map construction for our compounds. So we decided to choose some geometrical and chemical factors to be exploited, and among these valence electron valence concentration VEC parameter, the electronegativity from Martinov-Bazzano, because it's very effective for inorganic crystalline materials, the very simple but intuitive volume contraction parameter by Merlo, and the effective ratio parameter introduced by Tsai and somewhat modified by us. In this plot, I give you the idea of combination of three of these, but probably the less effective is really the electron concentration one, because you have no clustering for your compounds. You have a clear separation between aluminum, magnesium, zinc, and other components inside, because they have a different number of valence electrons. So probably it's not a good choice for constructing the clustering for such a big class of compounds. But much more lucky, the combination of other three compounds between them, effective atomic ratio, volume contraction, electronegativity, etc. You can see that almost 90% of all approximants, they fit perfectly in the very range narrow of parameters I discussed before. So these parameters really could be used like a screening for monitor or prediction of existence of new compounds. Only 2 minutes, give me more, probably one more. I will dare also to give you some roadmap for new approximant and quasicrystal discoveries at this point. If you would like to target the quasicrystals of Mackay type, probably you should choose a combination of cations and anions, chemical elements in the ratio of 4:1. Please verify for this. You can already, from the combination, recover the effective ratio and electronegativity also from Bazzano-Martino. If they will fit to this region, probably it's a good idea to go further and generate some theoretical approximants with wanted composition and structure, and relax it with DFT to get the effective volume parameters. In this way, you can put 2 more plots and to verify whether they all the time fits within this circle. If yes, why not to construct a convex hull and see where the energy of your approximant will be with respect to the convex hull curve. Probably you will fit a good candidate. If it's only a few millectron volts per atom, probably you are going versus a successful experimental work to be conducted later. And you can verify your hypothesis doing an experiment. And probably you would be lucky to discover a new approximant, and if you are so lucky, also quasicrystal in this system. So I went to the end of this presentation. Thank you very much again.
Thank you very much for the beautiful presentation and also well organized in time. Now we have some time for questions. Please.
At first, compliment for the very nice presentation, for presenting clearly this, let's say, very complicated landscape. My question is, in the data mining and in the search for quasicrystal, this relatively new tool like principal component analysis, multivariate methods, or the old-fashioned artificial intelligence daemon, could they help in this search and in suggest maybe correlation?
Thank you. It's a very good question, also a philosophical one. This presentation I did by myself. I did not use artificial intelligence. So I'm a bit aware about the capabilities of this, but I also could not neglect that it goes further. It develops so quickly that probably it would be happen one day also to use some routines done by artificial intelligence. But the question is to teach them. And this material as a new material, so these are new data. So let's explore a little bit and later let's teach it correctly how to do it. If there are someone, teacher, for doing this, it would be great. I don't know, it may probably will require too many efforts from my side, but why not? Let's do it.
Other questions? Curiosity-driven questions? Prego.
Just a comment, Pablo. Thank you very much for your talk. And I would like to know the size of the crystal you analyzed by single crystal diffraction.
You know, they are excellent scatterers, so it was like something like 10 micrometers or even 12. They are well shaped. You have no problems. And probably you are also wondering whether some super reflections of some aperiodicity we found. With normal laboratory diffractometer, not. But I do not exclude that it may happen, and this disorder phenomena could somehow have some reply also in the superspace or some way we function. Who knows? It should be explored probably later.
Yeah, this is the reason because I asked it. Thank you.
See that we have no other questions or comments, so we thank you again very much. Prego. And now we have a contribution from the University of Florence, Fabio CINTI, who will tell us about many body physics of bosons in quasicrystals. Prego.
Thank you very much. First of all, I want to thank Professor Bindi and the organizer for giving me the opportunity to talk in this beautiful room. I'm quite intimidated by the fact that here, stopped by Lagrange and Avogadro. I mean, it's something for me quite amazing. So thank you also for giving me this emotion. I would like to change a bit the point of view of quasicrystal in the sense that I started with other guys to the idea to work with quasicrystal in many-body physics. And I'm trying to... Is it working? Yeah. So with me are working quite a lot of collaborators. I want to, for this reason, thanks Vinicius Zampronio Pedroso that is working in this subject, and also Matteo Ciardi, that was a former PhD in Florence and now is a postdoc in Vienna, and also, in particular, Alessandro Mendoza Cotto, on which we share a lot of idea regarding quantum many-body system in quasicrystal. So, let me start with some motivation. I have to click this one. Okay, you know way better than I do the beginning of the tale of quasicrystal. But now there are some groups that start to think about how this can change the quantum properties of many body systems. In particular, I'm thinking about bosons, so quantum particle that obey to Bose-Einstein statistics and with spinless, without degree of freedom. So the idea is if you take the aperiodicity, you eliminate the block theorem, and you have a physics from our point of view similar to a disorder or quasi-disorder system. And here the idea is combine the behavior of superfluidity with multi-length scale inside the idea of two-body potential, so a simple two-body interaction. And another important thing is that quasi-periodicity can create Bose glasses, which essentially are superfluid that survive in puddles inside the crystal, exactly like a classical glass, okay? And another point of view is, of course, try to match the idea of quasi-periodicity with supersolidity, which is something that in our field people start to think about. A supersolid basically is a phase that remains crystal, but at the same time has the property of superfluidity. So at the end of the talk, I will have a little sketch that explains this. So it's quite simple, the idea, but it's very difficult to prove that exists in laboratory, okay? Recently, there are a lot of, as I said, idea like in cavity, in optical crystal, in photonic, okay? But I'll take just an experimental example. So in Cambridge, the group of, sorry, I forgot the name, the group of Schneider, okay, Ulrich Schneider, is able tuning different independent laser, is able to create an optical lattice which is quasicrystal. In this way, there is this situation where locally we have disorder due to the fact that the potential change, the depth of the potential of this quasicrystal change one to another in the small region, okay? So we might go from what we call Anderson localization to a Bose glass phase where there are regions that are superfluid, but they are not able to communicate among themselves, to a simple superfluid phase, so a frictionless fluid. Please think only about bosons, okay? About fermions, afterward we'll have an expert that will explain this subject. And an open question would be how this lack of periodicity, introducing longer range interaction, can change this kind of phases. So this is the main idea. The many-body physics is a quite complicated subject, and we face this using quantum Monte Carlo. Okay, quantum Monte Carlo is a huge subject. Essentially, we can study this at, this is the Wikipedia page, we can study this at t equal to 0 and at t different from 0. In particular, I'm going to try to explain you the taste of the path integral Monte Carlo, where taking essentially the idea of Feynman, of quantum physics following by Feynman, one boson is a necklace. Okay, don't confuse this with strings, that is another subject. So the delocalization of the particle can be explained as a string, as a necklace, okay? So the idea is sampling the partition function of the system, because we are working in finite temperature, not only in a real space, but also in imaginary time. So the temperature becomes imaginary. There are many techniques that are able to allow us to simulate a system and essentially to extract quantum properties, okay, like superfluidity, condensation, and also the structural property that for us are very important to analyze. Okay, for me, quantum Monte Carlo, as I said, is this collection of necklace, each of them representing a bosons, okay? In the real space, thinking two dimension, okay, I'm simulating the de Broglie wavelength of this particle, okay? The more these regions are large, the more I have delocalization. So I have, think about the condensation, the superfluid fraction, okay? And in the Monte Carlo, this is what happened. So I have a word line that's simply sampling the continuum space. Okay, this is the idea of quantum Monte Carlo, using path integral Monte Carlo. And now I want to tell you how we use this technique to study bosons in quasi-periodic lattices, and we create in our simulation exactly this quasi-periodicity with this local disorder, exactly like the experiment I mentioned you before. And we want to study, of course, the diffraction pattern, the superfluid local. We are able to study the superfluidity locally and also globally, okay? I put here the formula. We are going down and counting. We are sampling the area that are swept by all these tangled bosons. So it's not simple to understand, but it works. So it's a very well stable tool to study superfluidity. And also is also important the compressibility of the system that allow us to understand if we have a Bose glass or not, okay? So using the diffraction pattern, so the main idea of our simulation is just throwing bosons in a quasi-periodic lattice and see what's happened. So all these here are the delocalized particle that, in this case, we have a sort of superfluid phase because the lattice is not so deep, it's very shallow. So the more is deep the lattice, the more we will have localized boson in a quasi-periodic lattice. Okay, so we have this configuration and we throw bosons that, as I said to you, are basically necklace that sampling the space. So this is the main idea. Okay, looking the diffraction pattern, moving the depth of the shallow lattice, we can go from a superfluid phase, we go here, around here, you see, where the peaks are broad enough to leave bosons communicate throughout the system, okay? In the superfluid puddles, where I observe the superfluid puddles, what I call Bose glass, these peaks start to be connected among themselves, okay? And of course, if I increase enough V0, I have an insulating phase, okay? But this happens every time on a quasicrystal structure, okay? It seems that bosons can survive in this configuration. I'll tell you something about the quantum properties. Okay, so again here I'm going to a temperature which is lower than the condensate temperature or superfluid in the case where I don't have any quasicrystal inside, and we can simulate locally the superfluidity and the compressibility. Okay, essentially in this region, okay, here. We have a superfluidity which is unitary, and at the same time the compressibility. So the system is completely superfluid. Okay. Again, increasing the depth of the potential, we go in a region where K, the compressibility, is strongly suppressed, but the superfluidity is still present. Okay. So this is the case of Bose glass. Again, increasing V0, again, we have a perfect classical quasicrystal in this lattice. And we are able to observe this phenomena in each of this zonal region. Okay, we are able to check the quantum properties quite in a precise way. So, and of course, I try quickly to show you a phase diagram increasing the temperature that might be helpful also for experiment. So we can go from superfluid Bose glass at lower temperature to insulator eventually. And at high temperature, of course, we have a normal fluid. Okay, so this is a sort of phase diagram that, as I said, can help the experiments. Okay, here I will show the only Hamiltonian of my presentation. So we try to remove the disorder. So in this case, try to simulate bosons in a perfect crystal that we learn how to build in our quantum Monte Carlo using an Hammam-Benker tiling. And in this way, the Hamiltonian that we use is an hopping term, so the kinetic term, the quantum term, that helps boson to jump from one side to another, and also a potential, a short range potential. Okay, it's not a long range potential. And here, moving chemical potential, and again, the V, we can go throughout very interesting phases. Of course, we go from a condensate delocalization, where you can see also to the color scale, all particles can be delocalized throughout the system. And another interesting phase is a Bose glass where superfluidity remain inside this wheel. Okay, so wheel host the delocalized particle, and again, increasing the chemical potential, we go through a modulated phase without condensation. We still haven't understood this last phase, so it's still matter of research. But I want to focus, okay, this is the phase diagram, you know, we can distinguish mainly about two different phases, okay? Bose glass, a condensate fraction. This phase diagram has been built in a ground state. Basically, in the path integral Monte Carlo, we decrease the temperature up to the moment in which the energy is constant. Is always so. We say that in a way we build the ground state. Okay. Otherwise, it's complicated. We have to use other methods. But in any case, the condensate fraction is built by the one-body density matrix, which is a quantum object that is used in many body physics. And again, here we have to use the compressibility to understand if we are talking about, as I said, Bose glass. Okay. So let me focus on this nice picture. And I want to put your attention, here we have these wheels, and as I said if we go to analyze the evolution in imaginary time of the word line that represent our bosons, we see that inside the wheel, particles are delocalized throughout the system. So, and throughout this eightfold rotational symmetry of the quasicrystal. So this means that indeed, inside this wheel, there is superfluidity, and all the rest is a crystal, is a quasicrystal. So if I remove the disorder, I'm able to have a Bose glass, and this is quite remarkable from my point of view. But it's the first time that someone saw this behavior. Another important thing is that the global condensation of this system goes to zero when I increase the pattern, okay? So as a Monte Carlo, I need to increase the pattern and obtain a finite size scaling in order to understand the homogeneous situation. Okay, so another important element of this study is the connection of quasicrystals with long-range interaction. In our field, there is a lot of study related to the dipole-dipole interaction, okay, which is long-range enough to create what it's called clustering, okay. Dipoles becomes in a certain, choosing the right parameters, can form clustering of dipoles, okay? Because the interaction is strongly anisotropic. So if they are able in lab to tune the scattering length, they are able to stabilize this kind of structure. And this structure, as I mentioned you before, are super solid, okay? Of course, the zoology is start to be very interesting because we don't have only triangular structure made of these clusters, but we have also kind of stripes, we have honeycombs, and this kind of configuration are obtained just tuning the density of the system together with the scattering length, which has to be compared with the dipole-dipole interaction of the atom. So it depends to the element that we are to study. So here the problem, it's a little bit more complicated. It's quite difficult to study with Monte Carlo. And for that reason, we use the mean field approach for now. So we are trying to simulate with quantum Monte Carlo this system. But for now, I show you only mean field results. Essentially, we have an energy is a functional that we have to minimize choosing an ansatz of the wave function. Okay, it's basically solving the so-called Gross-Pitavesky equation, the generalized Gross-Pitavesky equation, because together with the dipole-dipole interaction that I have written here and the trapping that is necessary to confine these particles, we have to add other terms that are called Lee-Wan-Yang terms that allow us to stabilize the structure. Okay, using this minimization process, because essentially we are going to solve differential equation, we have a sort of local disorder, as I showed you before, that guides quantum transitions. Okay, and we can go here from triangular super solid, which means I have a crystal structure that is connected coherently to all the other crystal structure around. We have also a stripe phase, which is superfluid as well. And the most important thing of this work is that the quasicrystal structure of bosons seems to be super solid as well. Okay, we have this superfluidity that coexists with the quasi-periodicity of the lattice. Okay, this has been done, for instance, increasing the depth of our potential. And how much time do we have?
5 minutes.
5 minutes, okay. So as you can see in this region, okay, the delocalization of these droplets are very well defined compared to the region where quasicrystal has a sort of local disorder in this violet part. Okay, so also in this case, our effort is trying to build phase diagram that perhaps can be used in the lab to observe this kind of phases. So for now, I say thank you for listening, but I owe you what is a super solid, okay? Because maybe some of you did not understand very well this concept. And I try in this few minutes with a cartoon. Okay, suppose that you have a set of bosons, okay, in a free space, with a potential, a general potential that decay like R to alpha, okay, something very simple. Or you can think also to a soft core potential, something very easy. And you start to increase alpha, the interaction. And in this case, you have only a superfluid phase where particle can be delocalized everywhere in the system. And then you start to increase again the interaction. And they start to clustering due to this potential, very, very simple representation. But what is important is that the superfluidity remain between 0 and 1, and this means that bosons remain localized in the droplet, but they are also able to delocalize throughout the system, and this is directly connected to superfluidity. This is a toy, is a plot to represent a typical supersolid. Of course, the idea that superfluidity have to be between 0 and 1 is a formal result obtained by Leggett many years ago that proved that if there is a breaking of the symmetry, the superfluidity is not completely 1. So, and this is the first footprint of a supersolid. Of course, if we increase again the density, the interaction, we go in a perfect crystal of clusters, where all particles remain superfluid inside the cluster, okay? So let me come back, and now I finish my talk, and I thank you for listening.
Really very interesting. Questions, comments? I have a question. When you send quasi-periodical optical lattices from different directions, not in 1D, then you have the quasicrystal in which dimension? 2 dimensions, 3 dimensions?
In this case, you have to think about 2 dimensions.
2 dimensions.
Yeah. Yeah, I mean, the physics is for 2-dimensional system, although you have this potential.
So it's in 2D.
Yeah. Basically, this guys here. Let me see. Here. So basically, you are studying the superfluidity throughout the system in 2D.
So this makes your insight more important, because 1D or 3D, one can predict what happened easily. In 2D is
well, physically, this one is 3D, but the delocalization must be seen in 2D.
Yes. And so I have now another story. Suppose that you want to really to see periodical lattice, but in super solidity. If I understand, you would, if you think to the experiment that one does putting the bichromatic optical lattices that you mentioned on an atom, then to see this, we should add some long-range interaction between the atoms, or not?
You already have the dipolar interaction, and you have to
Yes, I know the dipolar, yes, but then
you have to try to cross laser in order to create a quasicrystal. So, because my idea was
okay, the experiment of dysprosium, for instance.
Exactly.
You at this point you should simply add the bichromatical optical lattice to induce a quasi-crystal, but well, we can discuss it. Really is.
No, exactly. I mean, the point is that you already have these guys here, so try to cross the laser in order to create a quasi-periodical lattice.
Okay.
And perhaps.
But I see that I have my mentor.
To follow on the question by Massimo, so is in this physics. So, I mean, you're considering quasicrystals, and so with some, quasi-periodic topology of the position of sites. So, what could change if instead of having some positional quasi-periodic arrangement, you have some, diagonal quasi-periodic arrangement of the energy. So it's supposed to have a kind of square lattice or another kind of, positionally speaking, ordered crystal, but with some diagonal quasi-periodic modulation in the energies, on-site energies.
You have a competition between the lattice and the structure of these dipoles, of these clusters. And probably you might have regions where maybe you might have another Bose glass. I'm not sure, but it seems.
I think that is a complicated but also very interesting
No, but this
story.
is easier. So
because
maybe
when you create,
easier, yes.
you think to the Josephson excitation that we observe in the supersolid. The supersolid organizes itself with a lattice, and then you have the fluid part. Now, if instead he adds with some bichromatic thing another lattice, which is we should think to this, because we could produce an incommensurate second optical
this
lattice.
is the idea.
Okay. But now too many curiosity from the collina di Arcetri, and now I think so. Grazie, ciao.
Thank you very much.
And now from Florence to Florence. Actually, from Arcetri to Sesto Fiorentino, Leonardo Fallani, who will talk us about ultracold atoms in optical quasicrystals. Che bello.
Okay, so thank you, Massimo, for the introduction, and so I'm really happy and honored to be here in this wonderful hall full of history, so many thanks to the organizers for the invitation. And okay, so today I will tell you how my research interests met quasicrystals and aperiodic structures, I would say 20 years ago. And so this meeting is about breaking symmetry, so crystallography and material sciences. So I'm mostly on the material science side, even if I will tell you of some materials that are not the ordinary materials that we are all familiar with. So these are materials made by atoms and light, as we have heard basically from the previous talk by Fabio. So this is what I will tell you today. So let me just say that, okay, I found all this world of quasicrystals really fascinating because it really lies at the intersection of many disciplines, from crystallography, we have heard, chemistry, physics, mathematics, and also because of that, I would like to be very introductory in my contribution. So for the experts, so I'm a physicist, of course, and for the physicists in the audience, so please forgive me if I will not give you the whole details of the story. So I'd like mostly to address those of you who are not familiar in the field. Okay, so let me start with just some. Just first slide, something that we all know very well at this point. So about the physics and the beauty of quasicrystal that in some sense interpolate between the physics of crystals, in which you have periodicity and long-range order, and the physics of amorphous systems, in which you have no periodicity and just some short-range correlations, but not long-range order. So quasicrystals have this very peculiar property of having no periodicity but long-range order. And for what I will like to tell you today, so I will mostly focus and start with an introduction on the electronic properties of such materials. So from the point of view of quantum physics, one is interested in trying to figure out how electrons, so quantum particles, can move in quasi-periodic structures. And of course, the kind of questions that arise are, what is the effect of the quasi-periodicity on the electron conduction, or do the electrons localize by the by the absence of periodicity, but long-range order that you have in a quasicrystal. And so about 20 years ago, with Massimo, we were driven by the idea of trying to study experimentally in a control system that's very important and very general phenomenon in not only in quantum physics, but most broadly, in a much broader sense, in wave physics, that is Anderson localization, that is connected with the physics of disordered systems. So this is a famous paper by Phil Anderson, then he got the Nobel Prize in the 70s for his studies of the impact of disorder on the conduction properties of material, that if you put, depending on dimensionality and strength and kind of disorder, so disorder can turn a metal into an insulator. And what is the idea? And if you read the paper, so the kind of Gedanken experiment that Anderson had in mind was the following. Before that, let me show you what is the kind of model that that was described and studied by Anderson in his work. It was a kind of tight binding lattice model. For the non-physicist, I just would like to briefly explain what happens. So this yellow line models a kind of disordered lattice potential. So the quantum particles, the electron, experience a lattice in which not all the sides are the same, and they can move in this kind of disordered lattice by quantum tunneling. So with this J measures the probability for the particle of tunneling from one side to the next neighbor, and delta is an energy scale that accounts for the amount of disorder in the systems. Delta equals 0 means perfect crystal, so with no disorder. Finite delta means that all the sides are a little bit different from the others. This is a kind of diagonal disorder, not really positional disorder. And what are the effects of this? So this is the idea that Anderson had in mind. If you take one, supposed to have one electron in a really periodic and fully ordered crystal, and you let this electron feel free to move, to evolve with the system. So what you expect is naturally, so this particle will hop and will jump from one side to the next neighbors, and so it will spread over whole the lattice. So if you wait for a time that is long enough, this electron would have reached any position in your crystal. Instead, if now you consider some disorder, so in the form of this random energy offset in the system, so what Anderson found is that under some conditions you can get a localization, in the sense that even after an infinite amount of time, this electron will get localized and remain in a finite region of space. And this happens because of quantum interference effects of the wave function that destroys the propagation in the lattice. Okay, so now, of course, a question arises when you consider what happens if you don't have a really random disorder, but you have some correlations. In particular, if you have some long-range correlations, as it happens in a quasicrystal. And so this is a kind of a variation on the Anderson model that I will show you in a moment. We realized already several years ago experimentally, and I will show you with which kind of platform. So you can think of modifying this model, this tight binding model, with some energy offset that now is quasi-periodic, in the sense that you have some periodicity with wavelength lambda 1 of the supposed to consider now a one-dimensional system. So a lattice with some period lambda 1 and these modulations of the energy with a non-commensurate wavelength, so you lose periodicity in the system. But still you have long-range order because you can deterministically describe the energies of each side. And this beta is an irrational number. That means that you have no periodicity, no recurrence no super lattice periods in the system. And so this problem was studied theoretically in the 80s by Serge Aubry and Gilles André. In this paper that was kind of unknown, stayed rather unknown up to 2007, 2008, when we started realizing experiments and probing that these predictions of this paper were really valid. And so now it has become some kind of highly cited paper. And what is the idea here? And let me summarize here the main predictions of this paper that also nicely show how quasicrystals, quasi-periodic structure, more broadly speaking, interpolate between order and disorder. And then I will move to experiment. So what you see here is for the non-physicist of you. So this graph represents on the horizontal axis the position along this one-dimensional system. On the vertical axis, you have the strength of this energy modulation. In the case of a periodic modulation, of a random modulation, of a quasi-periodic modulation. And so you can see here a kind of interesting behavior. So if you have periodicity, so you can get, for whatever perturbation strength, so this this color scale measures the capability of a particle to delocalize. So if you see here color everywhere, this means that the particles can move in the lattice. So this is the modulus of a wave function of the electrons in the system. In the case of a random system, you get localization, as we have seen before. So in 1D, even in infinitesimal amount of disorder can localize the wave function exponentially, and you can see here that for any finite perturbation strength, you can get localization. But here you see that quasi-periodic system exhibit a phase transition, a quantum phase transition from a behavior at low perturbation strength that is very different from the behavior at high perturbation strength. So if delta is sufficiently small, you have a metallic behavior, and so your quantum particles will be spread to delocalize across the whole lattice. If delta is too large, is larger than some critical value, you can get localization, so exponential behavior. So this is interesting. So you have in a one-dimensional system a quantum phase transition between two strikingly different regimes. So we're interested in studying this kind of physics, and so let me now tell you how. And this is pretty much connected to the talk by Fabio before, so let me just give you a few slides of introduction to the platform of cold atoms for those of you who are could be not familiar with that. So we are experimental physicists, we work with atoms and lasers, and so what you see here in this vacuum chamber, in the middle of this chamber is this green spot here. There's a picture taken in one of our labs at Lens and the University of Florence, in which you have a cloud of atoms, 10 to the 7, 10 to the 6, temperature of microkelvin, but we can get also down to the nanokelvin regime, so very low form of matter that exhibit a quantum behavior. So if these atoms are bosons, they can boson-condense, as we have heard before. And why can we reach this kind of very low temperatures? By using lasers. So by using lasers, we can take atoms as the atoms and the molecules in the air of this room and slow them down almost at rest. And when they are at rest, and for doing that, we need some kind of complicated laser equipment. So if you happen to be in one cold atom lab, you will find these tables full of lasers and optics, mirrors, lenses that are needed to cool your atoms, to manipulate them, to look at them, as I will show you in a moment. So everything looks pretty complicated, but one has full control on what you realize experimentally. So you can, in some sense, you kind of produce your samples. So these kind of, between quotes, materials are assembled by using laser light. And the main tool that we have here, and Fabio already introduced that, is the tool of optical lattices. So basically the idea is the following. You take lasers, and if this laser interfere, so they produce this kind of standing wave in which you have some maxima of light intensity, so it's just a cartoon, of course, and the atoms, when they are so cold, they can be attracted to the maxima of light intensity. So you can realize now that if you take just some monochromatic laser light waves, so this will create some perfect interference pattern, and so this means that you will create a perfect crystal with no disorder and no truly periodic with a long range order. And now the idea is what we call in our business quantum simulation, so to try to use this system, so this system made by atoms in this kind of crystals made by light, to study the physics of, for example, conduction of electrons in materials that can be crystals or, as we'll show in a moment, kind of systems which are close to quasicrystals. Okay, and of course the analogy is the following. So these atoms will experience a kind of potential, energy potential landscape that is produced by light, as the electrons in in the solid state experience the attraction to the atoms of a crystal. Okay, and let me just skip this. And so before showing you some results connected to the physics that I have explained to you before, let me just say that this idea of using atoms and optical lattice has been quite successful in the last, I would say, 25 years. And already to study the physics of, for example, some ideal solid-state physics, textbook solid-state physics. And so you have quantum particles in a lattice that you can control very well. You can control, for example, the tunneling amplitude. And so you can, and these are just some results that you obtained in our labs years ago. For example, you can see that really these atoms in these lattices behave as the electrons in solids, so you have energy bands. And you know that energy bands are fundamental to explain conduction in materials. You can measure transport properties, so not only ground state properties, but also you can induce currents and look at how fast, what is the velocity of the particles moving in these lattices. And you can also study quantum phase transition, for example, look at how a system that is, for example, in the non-interacting limit, a metal, or in the weakly interacting limit, a superfluid, in the case of bosons, can become an insulator when you have very strong repulsion between the particles. And let me now say that this kind of pictures that you see here with these are pictures of atoms, and this is basically the analogous of X-ray diffraction that we have seen in the previous talks. So this means basically when you see these kind of pictures here that your particles are delocalized in the lattice because they are quantum particles. And here basically you observe in a reciprocal space the wave vectors that corresponds to the reciprocal unit vectors of a lattice. Okay, and now, so we are at this meeting, we are interested in quasicrystals, so how can we break the symmetry of these systems? And so with Massimo starting in 2005, so we started these experiments first by exploring the possibility of really realizing some random lattices, for example, to observe undersea localization. So, and one can produce these by using some disordered distribution of light that can create some kind of random disorder. But then we thought that it was on the one hand easier, but also more interesting to study this physics of aperiodic structures. And so the idea was that we started to use in 2007 was to use these multichromatic lattices that indeed can provide the experimental realization of these quasi-periodic systems. So the idea is very simple. So if you have one lattice, as we have seen before, you have a truly periodic system. So now we can just superimpose another couple of laser beams at a different wavelength. So the different color of the laser beams creating the lattice with a ratio lambda1 over lambda2, which is not a ratio of two integer numbers, so it is an irrational number. And this produces an experimental realization of the Aubry-André model that I was presenting to you before, where we can control basically both these two energy scales. So by just changing the intensity of light, we can change the tunneling amplitude and we can change the amount of quasi-periodic modulation in the system. And so what we did, it was in these, the first experiments we performed in this paper here. So we basically did an experiment that was very similar to the Gedanken experiment by Anderson that I was presenting to you before. So take a particle, in this case not just one particle, but a Bose-Einstein condensate of many particles behaving in the same way. So put them in the center of this lattice and then look at how they propagate along the system. So we can just, look and perform some time-resolved measurements in which we can study and measure how these atoms will expand in this one-dimensional quasi-periodic lattice. And here we don't see the lattice because the lattice is so thin that this imaging system was not good enough to resolve the single size of the lattice. So this is some kind of coarse-grained density distribution. And here I plot the same kind of pictures as a function of time. So in the case of delta zero, so crystal, you have conduction, and so you have your atoms that can move, and the higher the time you wait, the more distant positions they reach in the lattice. But if you now introduce this quasi-periodic modulation, you see that at some point everything gets stuck. And so you have this quantum phase transition from a metallic behavior to an insulating behavior for some critical value of delta. And so this is an observation of, on the one hand, under-solocalization, one of the first the first observation of under-solocalization with matter waves, in this case for a quasi-periodic system and with this quantum phase transition that was predicted for quasi-periodic systems. And let me just say that we achieved this at the time together with a group of Alain Aspect and the group at Institut d'Optique in Palaiseau. Alain Aspect then Nobel Prize for quantum entanglement a few years ago, and you can see here a nice picture of Massimo, the Florence group, and Alain Aspect in celebrating this result. Okay, and let me, as I told you, I wanted to be some kind of introductory, so I will not touch then developments that might be probably too technical for this meeting. So, but I would like to say that this kind of system, was very rich and fruitful, and during the years we have investigated also other aspects. For example, the role of interaction between the particles, not with the dipolar interactions that were introduced by Fabio before, so some short-range interaction, but here we can study how under-solocalization is modified by the interactions with the particles. And also we performed back in 2007 the first experiments studying the physics of Bose glasses that emerge in this system. And we already heard that, so I will not tell you much more, but you can also, and this is the same paper that was shown previously by Fabio, using some kind of different lattice arrangements, create some quasicrystal positional configuration, and here you can study these pictures that are the analogous of X-ray diffraction, again, in the case of a quasi-periodic structure. Okay, if I have 4 more minutes. 5, okay, so you're so kind. I can tell you of a different story, so forgive me if in the last 5 minutes I will depart a little bit from the physics of quasicrystals, but this is somewhat connected, as I will show you now. So this idea of what I've told you up to now is about symmetry breaking, of course, and incommensurability. That is the key point in the physics of quasicrystal. So it is very interesting to note that if you take this Aubry-André model that I was showing to you before, the model of these particles hopping in this kind of quasi-periodic crystal, and you consider the energy spectrum of these particles. So quantum mechanically, what are the energy states that are allowed to these particles? You end up with this very nice spectrum here. So this energy, and the horizontal axis you have this incommensurability parameter beta. That is the ratio of the two wavelengths, lambda 1 and lambda 2. So this spectrum is famous in physics, is called the Hofstadter butterfly spectrum. And it was derived, and there is a very nice connection, I think. It was derived by Dag Hofstadter in the 76 in a kind of apparently very different system. So in this paper, he was studying a problem of quantum particles in a two-dimensional lattice in the presence of a magnetic field. So seems kind of a very different problem, a very different system from what I've shown to you before. This is basically what happens if you have the quantum Hall effect in a two-dimensional ordered crystal, for example a square lattice in this case, and you have a magnetic field, and if you have a charge particle as an electron, you have the Lorentz force that is induced by the magnetic field on these charged particles. And so you can see here that, the spectrum of the system is exactly the same. So even in this case, you have this kind of very nice fractal spectrum with these very dense gaps in the energy that appear. And let me say what is the connection between the two. And I find these are kind of very general features. So these fractal structures emerge when you have the interplay between two different length scales, which are not commensurate. So in the quasicrystal, or at least in the O'Brien-Drake model that describes this quasi-periodic lattice, you have two wavelengths. The wavelength that describes the position of lattice sites, and the wavelength that corresponds to the energy modulation. And a kind of similar thing happens in the case of a magnetic field, or a charged particle in a two-dimensional lattice, where you have a unit of area, that is the unit cell of your lattice, and the magnetic field that introduces an additional length scale, which is basically the area over which you have one flux of magnetic field quantum through the system. So I will not tell you. I will not tell you anything more than that. But just to tell you that you have this again this interplay between commensurability between these two length scales. I'm just telling this because in the recent years, and this is just another application of quantum simulation with atoms in lattices. And for those of you who might be interested, I can tell you that we can. This is something that we have worked in the last few years, engineer systems. I'm skipping some details here on how we do it, but this is a kind of, I would say, very nice and connected also to the previous talk, in which some kind of additional dimensions were introduced to explain the structural properties of quasicrystals, of aperiodic crystals, but I will not comment this point here. Let me just say that we can study this kind of systems and, for example, study with just another application of quantum simulation of atoms in lattices, studying physics of a Hall effect. And so there's some recent work that we have performed, observing, for example, edge currents that appear in quantum Hall system, and also to perform really a quantum simulation of a Hall effect in the case of strongly interacting fermions. So I will not tell you anything more. Just if you are interested in this kind of application of this platform, you have some references here, and here you can find the references that are mostly connected to the physics of quasicrystals. That is the theme of this meeting. Thank you.
Thank you, Leonardo. We have questions, comments? I must thank you because you made me a little bit younger, going back to this fancy, but I think that after the talks, this can be the interest for this kind of meetings, mixing people, because essentially with this artificial, if you want, crystal that we can do trapping atoms in light with the light, we can simulate things. And now listening to talks like the one of before or the others in real, mineralogy or solid state, we could try to get some inspiration for new adventures. However, if there are no questions, we complete now. We thank you.
Thank you.
And we complete the list of talks from Florence. with Luca BINDI, who will tell us about nature's secrets, nuclear wonders, and lightning. Enlighten us, please.
Okay, thank you very much, Massimo. Well, it's a pleasure. I think that most of us, have heard something about the discovery of quasicrystals in nature, but I will try to recount something which is a whole story and something which is occurring right in these days. So, well, a lot of people introduce what quasicrystals are. I will try to do something relatively different. We know that most of the crystalline materials we have in front of us are characterized by what is called long-range periodic order. Well, in quasicrystals we have this long-range order maintained, but it is aperiodic. So what does mean? So this means, well, you have a long-range periodic order. You can individuate a unit cell, which repeats in 3 dimensions, and in quasicrystals you cannot do it, because if you individuate a set of atoms corresponding to a unit cell, the other unit cell you have in front of, above and below, or on the left, on the right, will be different with respect to that you have chosen as your unit cell. So this does mean that you can have what are called forbidden symmetry, and indeed long-range aperiodic order materials. If you try to analyze this sentence, long-range aperiodic order, the fact that these kind of materials keep the perfect long-range order means that you can see strong and sharp diffraction peaks as the best of the crystalline materials. So look at this wonderful transmission electron microscopy of X-ray diffraction image. But the fact to be aperiodic means that you can see non-crystallographic symmetry axes. So these are, of course, what we call it crystallographic symmetry axis. And indeed, if you look 2, 3, 4, and 6-fold symmetry axis, covering, of course, a 2-dimensional floor, and 2, 3, 4, and 6, what about 5? If you try to cover a 2-dimensional plane with pentagons, which are governed by 5-fold symmetry axis, you are immediately stuck, because pentagons are not able to cover a 2-dimensional plane without leaving gaps and cracks among the tiles. So pentagons are governed by 5-fold symmetry axis, so 5-fold is a non-crystallographic symmetry axis. But unfortunately, this is what occurs in 2-dimensional plane. We live in 3 dimensions, and if you go in 3 dimensions, you got what is called the super forbidden symmetry. I mean the icosahedral symmetry, the symmetry of a soccer ball, where you can see 2-fold, 3-fold, and 5-fold symmetry axis respectively. Well, I think you all know that more than 15 years ago we discovered these kind of materials in nature, and this kind of materials was found in a small piece of rock belonging to the mineralogical collections of the Natural History Museum of the University of Florence. You can see on the bottom right of the slide the small piece of rock. And you can see different colors. Different colors correspond to different minerals intermixed together. And when we have different minerals, even if you have a small piece, it is a rock from a geological condition. Well, since we had, the quasicrystals was one of these blackish metallic materials you see in the image. And when we realized that we have a new chemical composition, a ternary alloy of aluminum, copper, iron, and a new crystal structure, we decided to propose this mineral to the International Mineralogical Association with the name icosahedrite, to reflect, of course, the internal symmetry. We got it approved, and so this aluminum 63, copper 24, iron 13 is the first naturally occurring quasicrystal. Well, a few years later, we demonstrated that this small piece of rock was actually extraterrestrial in nature. So it comes from outer space. And the main evidence we brought in the 2012 paper reported here is two main evidence. First, on the left of the slide, the discovery of a very, very high pressure phase in the meteorite. I mean, this is a silicon dioxide. I think that most of you know silicon dioxide occurring as quartz on our planet. But if you increase pressure up to 10 GPa, the structure of quartz became the structure of another compound, which is called stishovite, which is another mineral with silicon in six-fold coordination. So it's octahedrally coordinated, just demonstrated the density of the phases indicating the high pressure. More important, the 50 nanometer size stishovite grains containing inclusions of quasicrystals. And this was actually very important to individuate a strict relationship between a stishovite grain and the Florence Museum sample. But even more important, we were able to measure the triple oxygen isotopes of all the oxygen-bearing phases intermixed with the quasicrystals. And all the isotopes plot on what is called CCAM line, which means carbonaceous, chondrites, anhydrous minerals. I don't know if you know that carbonaceous chondrites are the oldest extraterrestrial objects we know, dated 4.57 billion years old, so the age of our solar system. So we had an extraterrestrial object, and since we have an extraterrestrial object containing the first natural quasicrystal, we decided to propose to the Meteoritical Society the small piece of rock as a new meteorite. And we got again it approved with the name Katirka. So Katirka is the first meteorite containing the first natural quasicrystal. Well, so at that time, you have to know that we got a lot of attention from the media, a lot of media coverage, it's incredible media coverage, because the discovery of natural quasicrystal was not important for geoscience only, but also for solid-state physics, condensed matter physics, and solid-state chemistry, astrophysics, and so far and so on. And so we decided to organize an expedition to the place where the Museum Florence samples came from. I'm referring to the place in far eastern Russia, beyond Siberia. So believe me, in the middle of nowhere. And we decided to organize the expeditions in order to refine new samples with this hope at that time. And I have to say that the expeditions was incredible from different point of view. But to make a very, very long story very short, we were able to find 10 new grains exactly identical to that of the Florence Museum sample. I mean, with the same alloys intermixed with the same silicates and oxides with the same oxygen isotope signature. And so you can imagine that these 10 new grains were characterized from all the techniques you can imagine. And I want to show you something. This is one of the grains we recovered in the expedition studied with the transmission electron microscope. This is one of the fib lamellae we extracted from one of these grains. And what I want to show you is, look at the ladders at the top left of the image. And these ladders are a combination, an alternation of two high-pressure phases. The first is a stishovite, you already know it, and the other is rhymboidite. So it is an high-pressure polymorph of olivine. I think you know it is a magnesium silicate, which is one of the most common minerals we have in our mantle, okay? So the presence of stishovite and rhymboidite, two high-pressure phases, and all the other petrographic features you can observe here are all indicative of a very high shock pressure, very high temperature, and even more important, super fast cooling. So with this kind of image, we proposed at that time, more than 10 years ago, the first hypothesis of formation of quasicrystals in space, I mean, as collisions among asteroids in outer space, who produce the conditions able to form these kind of materials. But you have to know that at that time, we were used to try to demonstrate all the hypotheses we had in mind. And for this reason, I started to search if some laboratories in the world was able to reproduce an asteroidal collisions in the labs. Well, I have to say that I thought it impossible. But actually, there is a lab. This is the Thomas Ahrens Laboratory at the California Institute of Technology, who is able to reproduce this kind of experiment. So they have a very, very long gun, which accelerate a projectile, a metallic projectile, at a very high velocity, I mean 1 kilometer over second. And the only thing you can choose is the target. So the metallic projectile is tantalum, metallic tantalum, and is accelerated over a target, which can be a single disk as a target, or a combinations of different disks stuck together. So we spent months to design the possible experiments, which is tremendously expensive. And at the end, we decide to use, look at the top left of the slide, 4 different disks stuck together. So look, an olivine composition, so an olivine disk with the olivine with the compositions exactly identical to that observed in our meteorite. Then a piece of copper aluminum alloy. Then a piece of Canyon Diablo iron nickel meteorite, so a very famous metallic meteorite. And then a piece of commercial aluminum bronze. Everything stuck it together and put in the stained steel chamber. Okay, and look at the white arrow. This is the shock propagation. So this is the arrival of the metallic projectile coming in this way. And look at these kind of blobs, okay? Look at these blobs here. This is a new materials formed during the collision. But we were very interested to look at the interface between the silicate and the copper alloy, so the metallic and the oxygen-bearing components, because we were interested to see what happens at the interface. So look at these regions, because this is a metallographic image. I want to show you a portion of this image. You rotate 180 degrees and look at the blow up here. This is the same region. This is the silicates and this is the copper aluminum alloys. Look at the interface here. And again, blow up here and again here. Well, with our surprise, at the very, very first shock, we produce an icosahedral phase with exactly, I'm saying, almost exactly the same compositions of icosahedrite in terms of aluminum, copper, iron. If you neglect the chromium and nickel components, which comes from a stained steel chamber, it was incredible. Well, we realized that the phase was actually icosahedral by means of field emission scanning electron microscope, I mean electron backscatter diffractions, where we observe 5-fold symmetries, okay? But since at that time, we were used to try to verify if actually the 5-fold symmetry distributions we observed with EBSD was actually real, I was able to extract a tiny grain, less than 10 microns in size, and carried out an X-ray single crystal diffraction study. You have to know that quasicrystals, even if they are very, very small, they are very highly diffracting. And indeed, I'm going to show you all the collected data from this small crystal down the 5-fold symmetry axis in mnemonic projections. And the image is actually terrific. Look at all the reflections. They fall perfectly the 5-fold symmetry. But even more important, look at the perfection, the structural perfection of the quasicrystals, which seems impossible because all the quasicrystals we produce in the lab are done with perfectly, rigidly, strictly protocol of formations. And here we are very, very far from equilibrium in a completely inhomogeneous medium, and indeed we produce these kind of materials. Well, if you want to get more information, you can find everything in this paper we published in 2016. Well, another critic we had in the last 10 years was that, well, especially from the NASA guys, this is the most arrogant community, especially if you are a geologist. Well, the NASA guys had to critique that, well, we studied meteorites and micrometeorites in the last 70 years, and we never found copper aluminum alloys. So, unfortunately, this critique is totally untrue and incorrect, because nowadays we have 5 different occurrences of these copper, aluminum, iron alloys from different parts of the world, and even more important, from different independent research groups. And you can see that we have Katurka, the first, and then the Nubian Desert in Sudan, and then Norway, and Saudi Italy, and finally the Democratic Republic of Congo. What is very interesting is if you look all these kind of materials, they are almost identical. Sometimes if you look the interface between the copper aluminum alloys and the silicates, you get the same redox reactions occurring at the interface. I don't know if you can see these small metallic droplets, which are mostly iron, indicating the same redox reactions. I don't want to explain, of course, here the geochemistry of the phases, but believe me, it is almost identical. But I want to show you something unpublished. If you try to put together all the oxygen isotopes of all the silicates of all the 5 occurrences in the world, you get almost the same signatures, indicating that probably you have the same parent asteroid producing this kind of meteoritic shower and of course dispersing all over the world. And so I think that we could find something bigger in some way. Well, so almost 5 years ago, in order to try to see new directions of this mega project, we start to think if these kind of materials could form in other conditions. I mean, well, we know that quasicrystals now can form in asteroidal collisions. We know that can produce in shock wave experiments. So the most clever idea could have been to try to search other transient states. I mean, other conditions around the world able to produce very high pressure, very high temperature, instantaneous changes of these kind of features. And for this reason, my mind went on atomic explosions and large impacts, and even more important, finally, lightning strikes. So let's start from the first, atomic explosions. Well, I think that you know well what happens in the morning of July 16, 1945, at the end of the Manhattan Project. The Oppenheimer group tried to test the first atomic bomb test, and the goal was to see if the detonations would be large enough to produce, of course, what happens in the days after in Japan. And I have to say that from the scientific point of view, the experiment was a success in terms the detonations was even much more larger than expected. But I want to say something unexpected. During the first detonations, which was carried out in the New Mexico desert close to Los Alamos, right? And during the detonations, part of the sand of the New Mexico desert was blown up in the atomic cloud and melted. And at the same time, all the metallic tools of the Trinity site, I mean the bomb itself, the tower surrounding the bomb, and all the metallic tools built to the Trinity test, well, of course, blow up and in the atomic cloud and melted at the same time. And you have the mixing between the silicate sand and these metallic tools. And these kind of features produce what is called the atomic rock, which is called the trinitite. I don't know if you know that trinitite is the famous rock testifying the first atomic explosions, and you have to know that there exist 2 kinds of trinitite, red trinitite and green trinitite. Green trinitite is almost boring, at least for me, because it is a silicate glass, okay, mostly silicates. And the red trinitite is more interesting because you have a silicate glass, but you have also copper, and copper is inside the silicates and is present also as metallic droplets. So I was interested to get all the red trinitites, and I think I had done the job because I have more than 300 red trinitite samples. And so I studied several of these red trinitites, and look at this. This is a selection. What I did, I took this kind of red trinitite, I put in epoxy, polished the surface in order to see the internal structures, to look for metallic droplets inside. It's a very long shot, okay, a very long work. But because the metallic droplets, you have to know, are relatively rare inside the silicate glass. Look at this transmitted light image. The red color is due to the copper present in the silicate glass. But you can see at the end of the white arrow the presence of metallic droplets, okay? These are, of course, high-resolution image of the red trinitite. So let's try to look at the small metallic droplets. Okay, this is, at the top you can see the composition in terms of a compositional maps of the composition of the silicate glass. So it is actually a calcium, silicon, aluminum glass, which is quite common. But if you look inside the droplet, this testifies how careful you have to be in order to carry out these kind of studies. Because if you don't look carefully, it seems that, well, it is a copper droplets. And indeed, if you look at the chemical maps, it is mostly copper. But if you look more carefully, you can see that the presence of sulfur at the borders, indicating that you have copper sulfides associated to the metallic droplets. But if you look even more careful, you can see that there are small metallic ternary alloys present inside the droplets, and in this case, a silicon-rich copper-calcium alloy. Well, I studied several of these ternary alloys inside several metallic droplets, inside several red trinitides, and one turned out to be a perfect quasicrystals. Look at again the 5-fold, 3-fold, and 2-fold symmetry axis reported here. And again, if you want to get more information, you can find everything in this paper we published 4 years ago. Well, what about lightning? I think that you know that lightning strikes can produce incredibly high temperature, and if you live, for example, in the United States and in Florida or in Nebraska, you have a lot of lightning strikes, storms, and something like this, especially in the beaches or in the Florida's beach. If you walk in a beach in Florida after a lightning strike storm, it's very common to find what they are called fulgurites, which are tubular aggregates of glassy materials, okay? Of course, I was interested in a very peculiar kind of fulgurites. I mean, a lightning strikes hitting a power line, and in the power line there is the metal conductor, right? And then you have the melting of the metal conductor with the lightning strikes. Then you have that the power lines goes down, and you have that when arriving on the road, you have a second electrical discharge who produce the melting of the silicates on the road. And you have the mixing of the melted metal conductor and the mixed silicates, which is actually seems very weird. It seems very rare, but it is quite common, especially in the old power lines in the United States. Well, I started my search and I found these fulgurites in Nebraska from the Sand Hills, which is a very wonderful place. And this is the fulgurite. So look at the tubular morphology. And look at the right part, there is a portion of the metal conductor. So I put a portion of this sample, this one, and look at this high resolution image. So this is the melted metal conductor, which is mostly aluminum and silicon, and this is the melted silicate, okay? If you try to look to the scanning electron microscope, this polished surface, you can get something like this. Look at the vesicles present, so indicating fast cooling, and look at the redox reactions occurring at the interface between the metals and the silicates, which is quite identical to that found in the Catturka meteorite. But what is very interesting is this testifies overline and how curious you have to be to find these exotic phases. You have to know that in the old power lines in Nebraska contains a core which is manganese and silicon enriched phase, which is put to increase the conductivity of the power line. Well, of course, during the lightning, you have the melting and mixing of everything. But if you look inside one of these holes, or the portion of the metal conductor, look at this here, and I will show you a blow up in the next slide. It is actually very, very interesting. This is a portion, look at this, and a blow up here, and again here, and here. So it is actually composed by two phases and a circular grain in a matrix. So we decide to FIB, by focus ion beam, to take two FIB lamella to study by transmission electron microscope. And the results are pretty amazing, because first I want to show you the chemical maps of the circular grains. Look at this. Look at the acicular grain, which are enriched in chromium, and depleted in nickel, which is enriched in the matrix. But what is very interesting is that when you try to cut it out and to obtain an electron diffraction pattern from the acicular grains, you got a perfect dodecagonal symmetry. So it is a quasicrystal, a dodecagonal quasicrystal with 12-fold symmetry. Even more important, if you look to the high-resolution electron microscopy image collected in Princeton, and look at the atoms are perfectly distributed along a 12-fold symmetry pattern. Let's try to decorate the high-resolution image. Look at this. These are the classic way to decorate. Look at the white dodecagons forming a large red dodecagons as perfectly observed in dodecagonal quasicrystals. But maybe you prefer to decorate with a classic motif we observe in dodecagonal quasicrystals, and you get something like this. And again, if you want to get more information, you can find everything in this paper we published 3 years ago. Well, so a lot of people encountering me asked, well, you find quasicrystals everywhere, but not on our planet. And so you have to say that we searched a lot in a lot of natural fulgurites, which is of course very important, or also in impact materials, but it is actually very complicated. But in the end, we found something which I want to share with you. Look at this new system, palladium, nickel, and tellurium. We studied these samples, which comes from Kalgoorlie, Australia, which is a very famous locality for the extractions of gold. So the most important gold mines are from there and in North America. And look at these small phases. Look at the bright phase here, which is a composition which is reported here. It is embedded in another phase, which is called melanite, which is a nickel telluride. And all the dark phases you see surrounding the phase are silicates, okay, which is the typical associations we found in Kalgoorlie. Well, when I found these compositions, I decided to extract the grain and carry out the crystal structure determinations. Well, what I got is something like this. Well, nothing surprising. It is an intermetallic, so we have 3 metals forming these kind of structures, so nothing serious. But if you try to analyze the structure in detail, you can get something curious. Indeed, if you look, for example, in this projection, and if you look to the orange atoms, which are the tellurium atoms, they are perfectly distributed along a 12-fold pattern. So it seems like what Pavlo told us before. So it is an approximant of a quasicrystal. So the classic gamma structures you can see here. So the tellurium atoms follow a 12-fold distribution pattern, but the other atoms follow the classic periodic distributions. So we have something which is going to a quasicrystals, but is still periodic. For this reason, since we have a natural mineral, we decided to propose to the International Mineralogical Association this phase with a very complicated name, I'm sorry, which was named proxy 12-foldite, because proxy means approximant, okay, approximant to a quasicrystal, and to approximant to 12-fold, so to the dodecagonal quasicrystal. And so this is the compositions. So this is actually important because in this system there are not reported approximant or quasicrystals. So it is actually a system which should be investigated, especially important because if you try to change the ratio between these elements, you can also find the quasicrystals in this system. Well, so finally, what I'm working right now. I'm sure that people present here really recognize what it is. This is a diamond, okay? And what you can see in black are inclusions in diamonds. Probably you are more used to see perfectly shaped diamonds. This is a raw diamond, but it is important because you have to know that diamonds are deeply studied in the mineralogical community because they are something like contains something like formed at very high pressures, and they are something like a capsule coming from the deep earth, and of course very important for us in order to have information of what happens there. But you have to know that inclusions in diamonds are very important because they can contain very peculiar compositions. Look at this. These are natural diamonds. And look, they can contain metallic manganese inclusions. And even more important, they can contain also inclusions of silicon, metallic silicon, manganese, nickel, and different distributions. Look at the different ternary alloys which can be present there. So you have to know that this is a composition of a metallic alloy, usually commonly found in several inclusions in diamonds. This is manganese rich with nickel. So you have to know that a composition quite similar to this one is reported to form dodecagonal quasicrystal. This was proved in 2015 by the Japanese colleagues. Perfect dodecagonal quasicrystal. So the idea is, try to synthesize a diamond starting from a metallic seed with a composition able to produce a quasicrystals, and see if the conditions used to form a diamonds are able to preserve and to form a quasicrystal. So it seems another impossible idea. So I decided to contact the guys who are able to synthesize diamonds in Russia, and one of them accepted and produced this kind of diamonds. They are relatively large, and of course I cannot give you a lot of information about this, but I can say that you can see huge inclusions in this diamond. Of course these are not quasicrystals because they are incredibly huge, okay, 200 microns. But if you look careful to this kind of other inclusions, something like these spherical droplets here, look at the blow up here. There are inclusions which are actually composed by two phases. And the metallic blackish phases turned out to be compositions which could fit what we were looking for. So this is what we are doing in these days. Well, at the end of this talk, I would like to give special thanks to all the persons who produced that I showed in this talk. And the first is my partner and longtime collaborator, Paul Steiner from Princeton University. And more than 15 years ago, we were two people working on natural quasicrystals, Paul and I and Paul. But nowadays, I'm proud to say that the team contains more than 100 members around the world working on this MESA project. Well, so thank you very much.
Luca, I was thinking that we really have to thank you for driving us along this journey among the extreme phenomena on Earth and in the universe, which, by the way, we started in the quiet place in Piazza San Marco, yes, side the monastery where Medici, Savonarola were simply thinking. So, in the secret of thinking well on what you have observed, what you have in your hand, really you can travel. So thank you, grazie.
Grazie a voi.
Now, questions, comments?
Thank you very much. I also congratulate. I just would like, I'm just interested in one thing you mentioned. If I remember, you mentioned that it's important, this rapid cooling or something is extreme, but is it always true? Because if I understood in the last case, you were not talking about rapid
yes,
cooling conditions. So
yes,
that's my question.
Yes, you're right. We thought at that time, that fast cooling was something like a necessary conditions, but you're right, it is not. But it is actually known that it is not necessary, because in industrial quasicrystals we produce by classic solid-state chemistry reaction. So you put the elements, the classic rigid protocols of the cooling down without anything super fast cooling or something like this. But it seems that at least probably the metastable compositions we found are probably need this kind of features, this kind of conditions, at least for what we have found so far. But I agree with you that, for example, the approximant we have found in terrestrial rocks does not need, of course, there are no fast cooling there. There are classic hydrothermal conditions. So thank you.
Thank you, Luca, for your interesting presentation. I just was wondering about why of the chapters you presented here about the lightnings. And doing experimental chemistry in my lab, for example, I have similar comparison with arc furnace we use. We have arc also inside. We have even arc for longer periods of time. So we can even change the atmosphere. We can mix nitrogen, oxygen to simulate the atmosphere of the Earth. So did you try to put some mixture of minerals and treat them by arc in the furnace in the lab just to see whether the result would be similar of what you found in the nature?
This is another interesting point. I actually did not try, but there are groups around the world who tried, I'm sure. But the problem is to analyze the resulting samples. This is the problem, because you have to be really, really careful. You have to analyze. It is a very time-consuming work. And so most recently it is a bit easier because with the advent of electron-based scattering diffractions, you can check very quickly your samples, your polished samples. But when you go to the very, very small scale, it is not easy. I think that you find them only if you are looking for them. This is, I think I learned in the last 15 years. But yes, I would love to make this kind of experiment. So if you are interested, we can discuss it. Okay.
So, again, very stimulating. All the session has been very much interesting. So we thank all the speakers, and we go to tomorrow.
Okay.